Hello children, your Vanasi ma'am is back with circles part 2. In my last class, I have revised a bit about 9 standard circles for theorems, and then I have discussed about the first theorem in standard 10, that is the angle which an arc of a circle or subtends at the center is double the angle that it subtends at any point on the remaining part of the circumference. So for that I have given you, just I am revising once again so that you remember. I have shown you suppose this is the center, this is the arc AB, and suppose okay, AB, arc AB subtends an angle AOB. Now the same arc AB subtends say any other angle in the remaining part of the circle. Okay. Suppose it subtends any angle in the I will draw neatly. Okay, this is the same point. Okay, so suppose this point I call it as say P. Okay, so according to this theorem, angle AOB is twice angle APB. Okay, so this P can be anywhere, wherever it is. If this P instead of here, suppose P is here, then also angle AOB will be double the angle subtended at P. If instead of there, say the P is here, so then also angle AOB will be equal to twice angle APB. Okay, and another one I told reflex angle, that is the angle subtended by the major arc. Okay, if AB is the minor arc, then APB is the major arc, right? That you already know. Now the angle subtended by the major arc at center O will be this reflex angle. Okay, reflex angle. So this angle, according to this theorem, if suppose I take say any point P in the remaining part of the circle, that is the minor arc, say, so then also in this case the reflex angle reflex angle AOB. This reflex angle will be equal to twice angle APB. Okay, so that is a theorem I explained you along with the proof also. Now the next theorem, theorem number 2 in your standard 10. It states angles in the same segment, angles in the same segment, of a circle are equal. Okay, now what does this mean? Segment, you know, I have discussed with you again, it is minor segment and major segment as there. Any chord divides the circle into two segments. Okay, now consider the figure. Okay, so AB is the arc. So the chord AB divides the circle into two segments. This is the major segment, and below AB you have the minor segment. So these 2 points, say C and D, they are in the same segment, right? So according to this theorem, angle ACB is equal to angle ADB. That is what we have to prove. Okay, so this can be proved using the previous theorem, right? So now, so what is to be proved? According to this theorem, we have to prove that angle ACB is equal to angle ADB. These are the two angles in the same segment, right? So proof now, before proof we have to do some small construction, that is join OA and OB. Proof now, angle AOB, which is the angle at the center, is equal to twice angle ACB is also equal to twice angle ADB, which implies angle ACB is equal to angle ADB is equal to half angle AOB, which implies angle ACB is equal to angle angle ADB. Okay, hence proved. So angles in the same segment are always equal. Okay, from examination point of view, this proof is not very important. The previous one, the angle subtended by an arc at the center is double the angle subtended by it in the remaining part of the circle. That is very important from proof point of view. The next theorem that I will be doing is again important in usage also, and in case of asking the proof also. It has been already asked, I think twice till now from 2015. The proof of this theorem has been asked, and this theorem is extensively used. So it states the angle in a semicircle, the angle in a semicircle is a right angle. Okay, so angle in a semicircle is a right angle. So suppose this is the circle, this is the diameter, O is the center and AB is the diameter. So APB and say AQB both are semicircles. Now according to this theorem, if you take any point say C, so any point in the semicircle, circumference of the circle, and if the angle subtended by the diameter AB on any point on the circumference of the semicircle will be 90 degree. That is, angle in a semicircle is always 90 degree. Right angle means 90 degree. Okay. So now we will have to prove this theorem. Now what is to be proved? To prove angle ACB is equal to 90 degrees. That is what we have to prove. Okay. Now proof. Again, this also can be proved on the basis of the first theorem that you have learned. Now, according to our theorem, angle AOB is equal to twice angle ACB. Okay. Now you have to write the reason here. Of course, in the first case also, in the other theorem also, you must write the reason. Never forget to write the reason. The reason for both is the angle at the center is twice the angle at any point in the remaining part of the circle. Okay, or remaining part of the circumference. The same reason we will have to write here. The angle at the center is twice the angle at any point in the remaining part of the circular circumference. So, but angle AOB is 180 degrees. Why? Because it's a straight angle. But angle AOB is equal to 180 degrees. What is the reason? AOB is a straight line. So angle on a straight line is 180 degrees. So this implies 180 degrees is equal to twice angle ACB. Okay. Suppose if this is your first point, this is your second point, this is your third point. So this from 1 it follows. Okay. So now this implies fourth point. angle ACB is equal to 180 degrees upon 2, that is 90 degrees. Therefore, hence we have proved angle ACB is equal to 90 degrees. Hence proved. Okay, children. Next. Now, before I proceed to the next theorem, I have to teach you about cyclic quadrilateral. Cyclic quadrilateral. First of all, what is a quadrilateral? A closed figure with 4 vertices, isn't it? Now, when such a quadrilateral is inscribed in a circle, inscribed in a circle means all the 4 vertices of the quadrilateral lie on the circumference of the circle, then the quadrilateral is called cyclic quadrilateral. Okay. Now, for example, the diagram is, suppose this is the circle, say A, B, C, D is a quadrilateral such that all its 4 vertices A, B, C, D lie on the circumference of a circle. Then the quadrilateral ABCD is called cyclic quadrilateral. So, when a quadrilateral is inscribed in a circle, that is what? That is the vertices of the quadrilateral lie on the circumference of a circle. The quadrilateral is called is called cyclic quadrilateral. Okay, it's called a cyclic quadrilateral. You understood the meaning of cyclic quadrilateral. Now we will learn some theorem